Hello, today's topic is central limit theorem. Okay, what is the central limit theorem, you ask? Well, it is a sampling distribution of sample means. This distribution is obtained by using the means computed from random samples of a specific size taken from a population. So when we have a set of data, we are going to have a set of averages that have been collected. So lots of data collected, it was averaged, we compile the averages, take a look at what that tells us. Okay, sampling error, and I've already filled this in for you, so if you need to pause the video, feel free to do so. Okay, so the sampling error is just the difference between the sample measure and the corresponding population measure. So like it's the difference between the sample mean and the actual population mean, or the sample standard deviation compared to the the population standard deviation, okay? So it's an approximation, the difference between the actual and what we've got in the sample. Okay, a couple properties of the sample averages. Okay, we're going to have that the mean of the sample is going to be same as the population mean. Okay, so we're going to interpret that to be the case. So mean, x bar and mu. Okay, secondly, the standard deviation, okay, our friend sigma, of the sample means, okay, so not just the data, but of the actual sample means, will be smaller than the standard deviation of the population. Okay, so it's kind of like the population standard deviation over the square root of the sample size is going to give us the population standard deviation. Okay, that's sometimes referred to, or is referred to, as the standard error of the mean. Okay, so what do we have here? So the actual theorem itself, the central limit theorem. As the sample size n increases, the shape of the distribution of sample means taken from a population with mean, and that little guy there that got question marked when I imported should be mu, and standard deviation sigma, which you've seen before, will approach a normal distribution. Okay, so what we have is mu is your mean, population mean. Okay, we're going to use standard deviation sigma over the square root of n, and that's going to adjust our z-score calculator to be x bar minus mu divided by sigma over the square root of n. And if you're putting all that stuff in at once, put some parentheses around that denominator. Okay, so the more sample means you have, the more likely it should approximate the normal distribution. Okay, all right, so let's take a look at an example here. Kids between the ages of 2 and 5 watch TV an average of 25 hours per week. Assume the variable is normally distributed and the standard deviation is 3 hours. If 20 children between the ages of 2 and 5 are randomly selected, find the probability that the mean Okay, I'm going to underline bells and whistles, okay? Probability that the mean number of hours that they watch TV is less than 26.3 hours. Okay, so here's what we have. We want the probability that the mean, so X bar, is less than 26.3 hours. Okay, so then what we do, and I'll do this off to the side, we want to convert that X bar into a Z-score, okay, using our new formula that we've just picked up in the last few minutes, this one right here. And yes, you can put that on your formula sheet. Okay, so we're going to have Z equals 26.3 minus the population average, which is this 25, all over 3 divided by the square root of 20. Okay, 3 being the standard deviation, 20 being n. Okay, if you put that in your calculator and divide, we'll take the z-score to 2 decimal places. It should be a positive 1.94. Okay, so now we're thinking, all right, we want the probability of z less than 1.94. Okay, so if I do a quick sketch in here, okay, so we're over here, 1.94. We want to be less than, so we want this and this. Okay, so either by table or by your calculator, a normal CDF. Okay, I calculated this to come out to be 0.9738 for the probability. You're welcome to say that is 97.38%. That's okay too. Either way, that's going to be your probability. Okay, perfect, using the central limit theorem. All right, let's go again. The average age of a vehicle registered in the United States is 8 years or 96 months. Okay, so average age, 96 months. Okay, average 96, that's your mu. Assume the variable is normally distributed with a standard deviation of 16. And again, months. If a random sample of 36 cars is selected, okay, that should be your n. Okay, find the probability that the mean, okay, so again, bells and whistles, woo, that's a big deal, the mean. As soon as it says that, we want to do central limit theorem of their ages between 90 and 100. Okay, so this one starts out, we want the probability of the average age of the car between 90 is less than the mean, less than 100. Okay, so we're between that number of months. Okay, so this time we have to convert both the 90 and the 100 into a z-score using our new formula of today. All right, so z is going to be 90 minus 96, 96 is the mu, divided by 16 over the square root of 36. 16 is the standard deviation, 36 is your n. Okay, so if you do your calculator math here, that should come out to be negative 2.25. Okay, then you do the 100, convert it to a z-score. Okay, so the z for that one, I don't know what happened there, got a little scribble going on my pen. Sorry about that. Fix that up here real quick. So the z this time is going to be 100 minus 96 divided by that same denominator, 16 over the square root of 36. This time, 1.5. Okay, so as a picture, we're over here at negative 2.25, and this side 1.5. And we need the probability, okay, for that area right in there, in between. Okay, so really it looks like this, where negative 2.25 is less than z is less than 1.5. So using your calculator, okay, to find that area, okay, I came up with 0.9209. Okay, I'm sorry, I'm out of room here. Or you could say it's about 92.1%. Okay, that would be your probability. Okay, sorry about the lack of space there. All right, then I have one last example for you here. Okay, it says the average of an, this one's actually kind of funny. The average number of pounds of meat a person consumes per year is 218.4 pounds. Okay, so the average pounds, 218.4. Assume that the standard deviation is 25 pounds and the distribution is approximately normal. Okay, part A. Find the probability that a person selected at random consumes less than 224 pounds per year. Okay, so my question to you is, did it say anything at all about the mean doing anything? Okay, it did not. Okay, so we will just do our plain old z-score just like old times. Okay, we want to be less than 224. Okay, so probability that x is less than 224. All right, so convert to z. So we will have 224 minus 218.4 divided by the standard deviation, which is 25 from up here. Okay, that's it. Okay, nothing else. You get 0.22 when you load that in the calculator. Okay, and we're less than. So we want to go from 0.22, deviations on the right, less than. So that's going to take us all the way back here to negative infinity. Okay, so if you load that in your calculator, normal CDF, okay, and run that through, I have 0.5871, or if you'd like to say 58.7%, that's okay. Perfect. Okay. All right, so then part B, what's up with that one? Well, it says if a sample of 40 individuals, oh, well, how about that? That's going to be your N. It is 40 instead of a person, which is 1, okay? Find the probability that the mean, there it is again, okay? Heads up, red alert, whatever you want me to say there. Woo! The mean of the sample will be less than 224 pounds per year. Okay, so this time you have X bar less than 224. So the mean less than 224 pounds per year. All right, now convert to Z using our central limit theorem formula that we picked up today. So 224 minus 218.4, so the tops are the same. The bottom is going to be 25 divided by the square root of 40 because we have a sample size of 40. Okay, so when you calculate this time, your Z should be 1.42. All right, so your little curve here, you are 1.42 standard deviations to the right. Okay, it's still less than, so we still want to go this way, shading all the way to negative infinity. Okay. All right, so when you do that calculation, your normal CDF and such, this time, let's see here, I came up with the probability of Z less than 1.42. I have 0.9222, or if you prefer a percentage, 92.2% would be the answer for that probability. Okay? All right, so again, this is central limit theorem. Okay, you use this adjusted formula, okay, for your z-score when you're talking about a distribution of sample means. Okay, please update your formula sheet accordingly, and I wish you the best of luck with central limit theorem. Have a nice day.